Hello everyone. I decided to make the videos on my vibrations playlist complete. Therefore, here I'm gonna go and add whatever topic that I did not cover. I'm gonna add videos for them to make it a complete course in vibrations. So I start with the very basics. In this short video, I want to talk about basically terminologies, basic terminologies in vibrations. The first one, that is the most important one, is if you have a harmonic function like a sine or cosine, there are four parameters in that sine or cosine function that are called amplitude, frequency, phase, and bias. And you can see all of them in this formula: x of t equals a sine omega t plus phi and plus b. So amplitude is the basically the total range of that function divided by 2. Okay, that's how much your signal deviates from its average value, which in this case for the harmonic function, that's this extra bias. So the average of a sine or cosine is 0. The sine and cosine, they oscillate around 0. But if you shift the signal up or down by amount b, so you see now the average of the signal is not 0, it's b units above or below. That is called bias. And then how much you are away from this b, your maximum is away from this, or your minimum is away from that, that is called the amplitude. Okay. Then we of course have frequency and phase. So frequency here, omega, which is measured in radians per second, is defined as 2 pi over t, and t is the period of the wave, which is the time it takes for the cycle to the function to repeat itself. And for sine or cosine is 2 pi, correct? So if this omega is 1, for instance, it's just sine of t. For sine of t, as I said, the period is 2 pi. So if you plug in 2 pi here, you see omega, which is this coefficient, should be 1. So you see it does make complete sense. And then you can also write it in terms of the frequency f, which is in hertz, or 1 over second. And in that case, that omega is written as 2 pi f. Okay, so your a sine omega t can also be written as a sine of 2 pi ft, or written as a sine of 2 pi t over t. Okay, so you can write it in any of these formats as long as your units are correct. So here that t is in seconds, this f is in hertz, that omega is in radians per second. Okay, the important thing is the unit of this guy here should be in angles, in radians, in degrees. Okay, so clearly radian per second times second is radian. Here you have 2 pi, which is already in radians, and this is 1 over t, and that t, they would cancel each other. Here, this is second, this is second, again, they cancel, and you get that radian. You see, so it is all about basically making that omega t of type radian, of type angle. And so, of course, you can have an initial start of phase, which basically forces the function to not start from the default position. For instance, the sine function at time 0, it starts at 0. If you shift it up, it starts at b. But if you give it an initial phase, you see right now it is not starting at b, it is starting a little bit off. So at time t0, if you plug in t0 here, your initial value, your x of 0, is basically a times sine of phi. So that value is what? This is a times sine phi. So the ratio of that over this is basically sine of phi. That is the phase difference, or phase, you might just call it. And that is where you start, basically, or how much your signal is shifted in the x-axis. So bias is how much your signal is shifted along y-axis. Phase is how much your signal is shifted along the x-axis. Okay, So these are the first four important parameters. And of course, the bigger the omega or the bigger the f, that means the smaller the t. So if a signal has higher frequency, you expect it to have shorter periods. So if I want to draw a signal with higher frequency, I have to basically do the cycles faster. And if I want to do a lower frequency, then I have to make the periods a little bit longer, right? So this is a lower frequency, but bigger what? Bigger period. So these are the first few important definitions. Okay, what else do we have? The next thing we have is the average of the signal, and many other places you see it's called the DC value. So DC value is simply the average of the signal, and that is basically the average of the signal over one period. So you integrate the signal over one period divided by the period, that is called the average for a periodic function. Now, if it's a sine function, the average of a sine function, even if it has a phase, is always 0. But if you add a bias b, then the average is going to be b. Okay, and that's exactly what you can see. Your signal is going above and below b, and your average is b in general. Okay, so the other thing you have is so the average shows how much your signal is shifted along the y-axis. The other thing is a measurement of basically how much your signal is away from the y-axis as it oscillates. That's called the root mean square, or RMS value. So here, because you have a bunch of positives and negatives, when you integrate them, these areas above and below the curve, they would cancel each other. You square them, then integrate them over one period and divide it by the period. And since this is of type signal squared, you take a square root of it to get something comparable to the original signal, or of type the original signal. So let's say if this x is in meters, you want to get x RMS to also be of type meters, not meters squared. So you basically average the square of the signal and take the square root of that. And for a sine function, you can show that the x RMS is a over square root 2. Okay, so if I want to show you that, what you need is to integrate, let's say, this function. Okay, so 1 over t, and then integral of basically a squared sine squared of 2 pi t over t plus phi, correct, dt, and then take a square root of that. This is what you need to do. So before you divide by t and take a square root, basically what you need to calculate is this integral, and this is integral of a sine squared, right? And so you know that sine squared of x is basically 1 minus cosine of 2x over 2, correct? Therefore, when you integrate this, you are going to get integral of 1/2, which is going to be x over 2, and integral of cosine of 2x over 2, and integral of cosine of 2x is 1/2 sine of 2x, but you have another 1/2, so you get 1/4, and then sine of 2x. Okay, so that's your integral. Now, in the case of this function, your x is all of this, or actually this whole thing is x, right? The only thing is, since you're integrating with respect to t, you have to pay attention to this guy as well, right? Because you have a coefficient, and your x, as I said, if x is that, then dx is going to be a little bit different than dt, right? If x is that, then dx is clearly going to be 2 pi over t dt, because phi is constant, right? So if you plug it there, you see that dt is clearly t dx over 2 pi. So here you have to replace that with this, and then you're going to get integral of, and a is constant, you can bring it out of the integral, so it's going to be just sine squared of x dx, and you also have that constant. So you are going to get integral of a squared, let's bring a out, over t. And then this integral is going to be, and remember this is from 0 to t, so it is going to be x over 2. And x, remember, is that whole thing. So it is that 2 pi t over t plus phi. It's that whole thing over 2. That's your x. And then minus 1/4 of sine of 2 times that. So it is going to be 2 times 2 pi t over t plus phi. Okay, that whole thing. And then you calculate it at t and 0. And remember, you have to bring in that other constant. So that whole thing is also multiplied by t over 2 pi. Okay, and from there you can see that that t and that t would cancel. That a comes out of the square root. A squared becomes just a. And so you just need to calculate this square root. So first you can calculate this at t and 0, right? At 0, it's just going to be phi over 2. At t, it's going to be 2 pi plus phi over 2. You subtract, it's going to be 2 pi. And then over 2, you're just going to get a pi out of this. And this other one is going to be minus 1/4 of, so sine of. So again, if you plug in t, it is going to be 2 pi plus phi, correct? Sine of 2 times 2 pi plus phi, and then minus sine of, basically plug in 0, is just going to be 2 phi. And you know, here, this is going to be basically 4 pi plus 2 phi, right? We also have this 2 pi that should come to the denominator. Now, since the sine function is periodic function, sine of 4 pi plus anything is the same as that. So this whole term is going to go to 0. And pi and 2 pi would cancel, so you just get a 2 under the square root. You bring it out, and guess what? You are going to get a over square root 2. Okay, so the a over square root 2, or 0.707 of the amplitude, is the RMS value for a sine function. And similarly, for any other signal, you can calculate the RMS value of it. Now, for energy of the signal, you have to integrate the signal from over entire range of its square of the signal. So for a sine function, it's going to be infinite energy, right? Because when you square the signal, basically it's just going to be all like this. And where these amplitudes are kind of a squared, depending on what they are, and they're all positive. So you're adding an infinite number of positive numbers, you're going to get infinite energy. Okay. Power, on the other hand, power, you know, it's the energy divided by time. So you can integrate the signal's energy over one period and divide it by the period, or you can have this t go to infinity as well, and then calculate it. Okay, so if you do it over one period, it's simply, as you can see, this entity here is the one under the square root here for x RMS. So you can say that power is simply x RMS squared when t is limited to a finite number. And for the sine function, basically that value is just going to be a over square root 2, the whole thing squared. So you're going to get a squared over 2. And whether this t goes to infinity or not, that's not going to change anything, because here we saw that when we calculated this, we saw that these t's would cancel anyways. So the limit will not have any effect on it. Okay. Therefore, you can say that the power for a sine function is simply a squared over 2. Now, many times when we talk about amplitudes, we measure them instead of directly in the units of the signal, we measure them in decibels. Especially, you probably heard that for sound waves. The way that you do it is you divide the power of the signal at the current amplitude divided by the power of the signal at a default amplitude. Take a log 10 of that and multiply it by 10. That is how you define decibels. Okay, and what does it do? Well, since you've learned that the power of a signal for a sine wave is proportional to the amplitude squared, so here these x's and x zeros are like amplitudes. So since the ratio of powers is proportional to the ratio of amplitudes squared, you can replace it there, and then log 10 of something to the power n, that power comes behind the log 10 multiplied by 10, you get a, there is a typo here, you get a 20, and then log 10 of x over x naught. So another way to do it is to divide the amplitude of the signal by a default amplitude, take a log 10 of that and multiply by 20, and that is what you do in many things in vibrations, controls, and so on, including Bode diagrams, that you see decibels. Okay, and let me combine it with the next topic, which is decade, and then I explain this graph here. Another last topic that we need to talk about is octave and decade. If you have any plots where the x-axis is a frequency axis instead of time, then if you go from any frequency to 2 times that frequency, it is called an octave, like you see on piano, for instance, right? When you play piano, you have octaves back to back. And then you have decades. Decades is when you go from any frequency to 10 times that. So for instance, if I go from 200 hertz to 400 hertz, that is an octave. But if I go from 200 hertz to 2000 hertz, an order of magnitude above, or I can go to 20, any of them is what? 1 decade. But here I have to go from 100 to 200 to 400 to be 2 octaves. So for instance, if you look at the Bode plot, you see this is a magnitude in decibels versus the frequency here, and the x frequency, if you look at it, in this case, it is really a logarithmic plot, right? So you see, it says the slope of this is negative 20 decibels because the unit of this guy is decibels per decade. What does it mean? Decade means you go from 1 frequency to 10 times bigger. It means in this range of frequency going from 10 to 100, the amount that it dropped, the amount that this magnitude has dropped is how much? Is negative 20 decibel or positive 20 decibel, depending which direction you do it. But then it became 40. So in this case, it's actually 40. So it's 40 decibel. But this portion here is 20 decibel over 1 decade. Then you go 20 decibel. Then you go 40 decibel. Okay, so over 1 decade, the drop is how much? The drop in this case is 40 decibel. So that's how you can interpret these Bode diagrams. Okay, so I stopped these basics terminologies here, but remember that in vibrations there are tons and tons of more terminologies. We have free vibration, we have force vibration, we have natural frequency, damp natural frequency, damping factor, resonance, there is mode shape, there is transient and steady state response, critical, basically damp, over damp, under damp, there is shock, there is logarithmic, decrement, Q factor, stiffness. There are so many things, okay? And I'm gonna go over them in the upcoming videos. So I don't want to tell you all about those terminologies in one video. I want to go over my, let's say, next video, which is free vibration of undamped single DOF systems. You're gonna see some terminologies Then we go over the damp response. You're going to get more terminologies, then force vibration, more and more and more. So I'm going to go over all of these remaining terminologies in my upcoming videos. Stay tuned. Thank you so much, and I'll see you in the next lecture.